Okay, so welcome back. Where we left off last time, we'd been talking about the uh, relationship between the dissociation curve and functionality of the pigment in question. Um, and one of the big things that we'd seen here in terms of the shapes of those curves was whether or not we saw cooperativity, right? With a non-cooperative arrangement, we had this sort of hyperbolic curve we see kind of here in this black line. When we have cooperativity, we have more of this sigmoid shape to it. And again, big changes there, right? What is the responsiveness of the pigment to changes in partial pressure, in oxygen concentration, right? Hyperbolic, right, will bind more oxygen faster, right? But the sigmoid one is more likely to release it at a higher partial pressure, right? So basically, the lack of cooperativity, like we saw in myoglobin, right, is all or nothing, right? We're either fully saturated at relatively low partial pressures, or we are completely disassociated. We have no oxygen bound at all. Whereas with cooperativity, we have a little more flexibility in how much we actually drop off. Now, if we look at different curves for different animals, we see that they vary in shape really in two basic ways. Now, part of this, right, and this is, again, a wide spectrum of animals. Mammals, reptiles, octopods, arthropods, annelids, all kinds of different shit. So one of the reasons we see different shapes in the curve is, again, because they have different pigments, right? They might have a chlorochlorine, like we see here in our annelid, helpfully labeled green, right? Or in any of our things that have these blue colors, right? We see things that are going to be our hemocyanins, right, versus hemoglobins, okay? All of which have different associations with oxygen, right? The other big difference that we're seeing here, and probably the biggest difference, one that leapt right out to you right at the beginning, is the height of the curve. And the height of the curve here is simply how much oxygen can be carried per unit volume of blood, or as we'll see, hemolymph or whatever. So different animals have different oxygen carrying capacities. The shape of the curve is going to be slightly different depending on what the pigment is. We're going to compare those different curves with something called P50, which is what this guy is right there. And what P50 is the partial pressure of oxygen when whatever our pigment is 50% saturated. Okay, so if we look to our percent saturation over here, right, we draw our little line where it intercepts the curve, we come down, that's our P50, it's the partial pressure. And for different curves, right, we're going to have different P50s, right? So for our blue curve here, our P50 is relatively low. For our red curve, our P50 is relatively high. Okay? What this means, right, is that a lower P50 has a higher affinity for oxygen, right? It binds it more readily and is less likely to let it go. A higher P50 has a lower affinity, and so it's less likely to bind it and more likely to drop it off. When we lower affinity, right, when we raise P50, right, this is what we're doing. We're having a right shift. So whenever we talk about a right shift in our curves, we're lowering affinity and we're raising P50. We talk about a left shift, we're raising affinity and lowering P50. And that's going to become really, really important for us as we talk about a couple of primary effects here. In particular, we talk about the Bohr effect, right? This is not what this lecture is having on you right now, right? This is the Niels Bohr effect. You might have heard of Niels Bohr, kind of a polymath, total nerd, would have loved him. But here this Bohr effect has to do with pH and partial pressure of carbon dioxide and the effects of those two things on the affinity of hemoglobin for oxygen. Okay, so with this one over here, okay, with Tina from Bob's Burgers, I guess. As we look at our curves for 3 different pHs, this one over here, more alkaline, this one in the middle is normal blood pH for a person. This one on the far right is a little bit acidic, so 7.6, 7.4, 7.2. What we're seeing is that as we get more acidic, right, as we lower the pH, we have a rightward shift. We are less likely to drop off, or excuse me, we're less likely to pick up oxygen, more likely to drop it off, the more acidic blood is. And the same thing's happening over here with partial pressure of carbon dioxide. As more and more carbon dioxide is present, our P50 increases and our affinity decreases. And so why, right? Why would any of this happen? Well, 2 things. Number one, these 2 are not unrelated. As we're going to see, when carbon dioxide goes into blood, goes into solution, it often forms carbonic acid, okay, which has the effect of lowering pH. So the more carbon dioxide, typically the lower the pH of the blood anyway. But there's a really valuable reason behind this. This is a very useful physiological tool for us. And that is to say, it's going to enhance our ability to deliver oxygen. Okay, so this is a wild diagram in a number of different ways here. So we'll kind of take it slow here. This curve over here with its low P50, right? This is arterial blood. And the curve over here with its higher P50 is venous blood, hopefully A and V. If we didn't have this Bohr effect, if we didn't have this rightward shift, we were stuck just with the curve here for our arterial blood, okay? Because our affinity is so high, right, we're not going to drop off a lot of gas, right? We might go from here in terms of our partial pressure, what we typically associate with, say, blood in the lungs, right, to down here. So we're taking our partial pressures from here to there, right? So we would take here, and we would look over here, right, and we would only get this amount of delivery, right? About 3.3 mils per 100 mils. The same is true here with their venous curve. If we were stuck just with our venous curve, right, we would have just the shift from here to here, right, which is a little bit more, right, because we've had this rightward shift where we have less affinity, but it's still only about 6.5 mils. Because what we have is one curve when we are fresh and naive and straight out of the lungs, and another curve caused by the Bohr effect, right? As we get out to our tissues, we deliver all of this oxygen, all the way up here, all the way down there, about 7.2 mils, okay? Take-home message, right, is because the Bohr effect raises the P50, okay, where we have little oxygen and lots of carbon dioxide, we're more likely to drop off oxygen where we don't have any oxygen. It's a pretty, I think, probably straightforward idea. You would think, okay, if I'm going to design something, it would work this way, but it's still a really important property. A related idea, although not exactly the same, is something called the root effect, named for a guy named Root, who discovered this. And the root effect is not something we see everywhere, okay? We see it in animals that have swim bladders, so a lot of fish, not all fish, but a lot of fish. We see it in the retina of the mammalian eye, the vertebrate eye, and not really many other places. And what the root effect is this idea that, okay, yes, as we have less oxygen available, we're going to have a Bohr effect, right? The Bohr effect is going to change the affinity of our hemoglobin for oxygen. What the root effect is going to do is it's actually going to lower, right, with increasing acidity, it's going to lower the maximum amount of oxygen that can be bound. Okay, we're going to lower maximum saturation. So if we look at our curves here, right, we're going to kind of plateau, right? But as we make the blood more and more alkaline, that plateau occurs at larger concentrations. And as we go more acidic, our plateau, our maximum saturation is less and less and less and less. So it's kind of an interesting little unique thing. We also see temperature effects, okay? So that higher temperatures result in a rightward shift and a higher P50 and a lower affinity, and a lower temperature has a leftward shift and a lower P50 and a lower affinity, right? All of these good things, right? Because where we're using oxygen, we're doing so through chemical reactions. Chemical reactions do nothing except generate heat, right? So a part of the body that's warmer is using more oxygen, and so we need to deliver more oxygen to those parts. The part that's cold is not using as much, and so we don't need to drop oxygen off there. In fact, we need to not drop oxygen off there. So again, this is kind of a self-correcting mechanism. It's a way of our body to ensure that oxygen gets where it needs to go, but not to somebody else. Okay? Now, imagine, if you will, our poor woolly mammoth, or our woolly rhino in the background there. Imagine our poor woolly mammoth's feet. Okay? Its feet are probably pretty cold, walked around in the snow all day, right? And in fact, we can get to a point where maybe the temperature of the foot is so cold, right, that we're way over here, right? Our P50 is really, really, really low. Is it possible that the P50 can drop so low that we actually don't drop off any oxygen? That our curve has shifted so far to the left that the affinity for oxygen and hemoglobin is so high it will never let it go? Yes. Okay. And so one thing really, really close, about it, maybe a decade old now. I remember I was in grad school, very end of grad school when this came out, and it was fascinating. But they were able to get E. coli to replicate. It's a whole long process. You can read about it if you want to. You can just search woolly mammoth hemoglobin. It's fascinating. But they regenerated woolly mammoth hemoglobin using E. coli to rebuild the protein. And they found that woolly mammoth hemoglobin has a slight alteration to it that makes it resistant to those cold temperatures. That even at really, really cold temperatures, it was still had a low enough affinity that was going to drop off oxygen to the tissues that needed it. So that was pretty fascinating. So far, right, we've looked at effects of carbon dioxide and pH, right, our Bohr effect. We've looked at temperature effects, right, on our P50. There's one other big factor here that we need to talk a little bit about, and this is a little chemical here called 2,3-DPG. It's a little protein. And what 2,3-DPG does is it raises P50, right? So it lowers affinity. So what we can find is that cells and tissues that require more oxygen, one way they can ensure that they get it, okay, is by producing 2,3-DPG in relatively large quantities. Or, right, if we're seeing a situation, this is much more likely, if we're seeing a situation where for whatever reason, our red blood cells are not delivering adequate oxygen, and there could be a variety of reasons for this, they can also produce 2,3-DPG and make it more likely for them to drop off oxygen at tissues. So if we take the whole thing together, right, we look at temperature effects, we look at 2,3-DPG, we look at Bohr effects, because of the shape of the curve, right, because it has this big, long, flat plateau here at the top, the change in the shape of the curve due to a shift, right, a rightward shift or a leftward shift, doesn't really have a lot of effect here where partial pressures are high, right? So what this means is that it doesn't really affect how loading works. Regardless of what our affinity is, regardless of what our P50 is, loading is loading is loading. We're always essentially going to be 98, 95% saturated when we leave the lungs. That's not going to change. Okay. The only place that we actually see a change, we actually see significant differences between these two curves, is over here in the offloading zone, right? It doesn't change the rate at which we pick up oxygen, it only changes the rate at which we drop it off. Okay, and again, that's really important for us. We really need to not have negative effects on our ability to pick up oxygen, because that would really kind of defeat the whole purpose of being able to drop it off. Okay, so that's oxygen. And we spent a lot of time with oxygen. We need to talk a little bit about carbon dioxide now. And here we've got another effect to worry about, and this is the Haldane. I don't know why that H is so big. The Haldane effect. Again, named for a guy named Haldane, big surprise. The Haldane effect is simply a way of explaining how hemoglobin picks up carbon dioxide. Okay, so hemoglobin loves oxygen, right? It really doesn't like carbon dioxide. It really isn't gonna pick it up unless it has to, right? And when we look at the way carbon dioxide is transported in the blood, really only a small part of it is transported as carbamino hemoglobin, or hemoglobin bound to carbon dioxide. But the little bit that does happen is driven by this Haldane effect. And basically the idea with the Haldane effect is it's like last call, right? Now, and I know all of you guys are model people. You would never go to a bar. You would never want to go to a bar to find somebody to spend some time with. But imagine if you were the sort of person that did that. You might go and it's 10 o'clock, the night is young, right? I'm old, so 10 o'clock is early for me. There's lots of people at the bar. You're gonna be a little picky, right? She's got weird teeth, he's got a bad haircut, whatever, right? At 2 o'clock in the morning though, right, her weird tooth and his bad haircut might not be a deal breaker for you anymore, right? This is the Haldane effect. So when there's oxygen, hemoglobin won't look twice at carbon dioxide. When there's no oxygen, hemoglobin might be thinking, well, gotta go home with somebody, and they might pick up some carbon dioxide instead. That's all this is about. However, most carbon dioxide is not transported bound to hemoglobin. Most carbon dioxide is transported two different ways. Some of it is dissolved in the blood as carbon dioxide, that is part of it, but most of it actually is transported as this combination of bicarbonate, I'm just going to say bicarb, okay, which is H2 CO2 and it has a reversible reaction with carbonic acid, which is HCO3 minus, that is a 3, believe it or not, and a free hydrogen. Okay, and so the reason that happens is we'll get into probably in the next chapter, depending on the time. But this is part of a buffer system. Okay, the shift between a free hydrogen ion or H2CO3 here, actually that's reversed. This is carbonic acid, that's bicarbonate. Whatever, I don't care. It's important, it's just not important right now. But this is the form in which carbon dioxide gets actually transported. The formation of bicarbonate carbonic acid can happen outside of the red blood cell. Okay, so it can happen out here just in the regular plasma, or it can happen, and this is where it happens fastest, is inside the red blood cell. So carbon dioxide actually enters the erythrocyte, the red blood cell, and then gets turned here into bicarbonate carbonic acid. The reason we talk about that here is that this stuff gets out of the red blood cell through exchange with chloride ions in the plasma. And this is called the chloride shift. That E should be there. I don't know what that's about. And then when we would go to the lungs and we start dropping off carbon dioxide, we have the reversed chloride shift where this stuff enters the erythrocyte, chloride gets kicked back down, whatever. Believe it or not, though, we actually don't exchange a lot of carbon dioxide with the outside world. The carbon dioxide levels in your blood are pretty constant all the way around, both in, there's a little bit of change, about 5 kPa, but not a big shift. So a lot of the carbon dioxide remains in your blood as carbonic acid bicarbonate, whatever. Okay, so we'll call it there. On the next unit, we'll actually talk about circulation. So we'll talk about blood vessels and hearts, and hemolymph and blood and all that kind of fun stuff. For now, we'll call this one good.